Hi, I'm Ben-Yaakov. This presentation is entitled BCM Converters by Triangular Current Injection, and this is part 1, basics of a two-part presentation. Now in this part 1 of the presentation, I'm going to explain the basics of triangular current injection to achieve BCM operation, and in part 2 it will include examples of application as published in some papers and evaluation of the injection method as compared to other approaches. I'm showing here a boost converter. Here are the two transistors, the inductor, the DC source, and here's the load. And this will be used to serve as a demo for a CCM boost converter, just to explain the issue of switching, hard switching, and soft switching. So if we look at the waveform of this converter, and here I'm showing the inductor current, the gate voltage of the lower transistor, and the gate voltage of the higher transistor, which is not of importance here, which I'm going to discuss primarily the lower transistor. And then I have also the voltage at the midpoint, which is basically the drain to source voltage of the transistor. So I'm starting here with a situation in which the gate is on, the transistor is conducting, and in this case the current of the inductor is rising because we have here the source, and here it's connected to ground. And again, I'm in CCM, so it's actually start with a certain current, and then it goes up to about a 9.3. Now at this point, this transistor is turned off, and since the current was going this way, then of course once I turn off the transistor, the capacitors, the output capacitors of the transistor are being charged, and there is a self-commutation here. It's basically this swing here going up from the low voltage or from ground to the output, and I call this switching pseudo zero voltage switching because we turn off the transistor as fast as we can, and then there is a sort of a slope here due to the capacitors here, and therefore, and I'm showing it here, there is some overlap, although this is not exactly, this is the current, but this is also the current of the capacitor, the internal capacitor. So we really don't see here exactly the losses due to the rise of the voltage here and the turn off of the current. Okay, so this is pseudo zero voltage switching. This is pretty good. And then we have the diode catching here because the current is going this way. So the diode is catching, and here we have now this loop here in which the inductor current is actually going down, and of course at this point we're going to turn on this transistor, and the upper one, which will be zero voltage switching, a turn on because the diode is already conductor. So this is fine up to the point the lower transistor is now turned on to switch from the upper to the lower transistor. Now here we have really hard switching because we have a diode which is conducting, since during the daytime we are turning off the transistor, so the diode is actually conducting. We turn on this transistor here, and here we have hard switching now, due in fact to two reasons. One, we have the reverse recovery of the diode, that is, current will flow the other way around, and then we'll have a spike. Here it is. Here, this is the spike, and I have actually a zoom here, and I can see here the spike. Now, in this case, I have no inductances here, so it goes pretty high, and in any event, in a real system, it's going to be a very harmful effect. And then there is another reason for the hard switching, and that is that this transistor now, once the diode stops conducting has to discharge, or charge you might say, this one, and discharge this one, these capacitor, and all the energy of these capacitor is now being dumped into the transistor, so we have another loss here. So in this case, in the CCM mode, we have hard switching, especially at the turn on of the lower transistor. To remedy this, we can use the BCM, or the borderline current mode approach, in which case we are actually causing the current of the inductor to go negative. In fact, by current reversal, we many a times correct problem of hard switching and convert them into the zero voltage switch. So in this case, the inductor is small, and consequently we have a very large ripple current such that it actually goes to negative. That is, after we turn off this transistor, current will be flowing this way. The diode will not be conducting because this is the reverse direction of the current. Okay, this is here, current is going this way. We are now discharging or charging this capacitor through the inductor. This is a sort of a lossless process, except for the losses within the inductor, but the process itself is lossless. So here we have a commutation, and the voltage at the midpoint will go down to 0, and when it goes down to 0, then we have the diode catching, and we have here soft switching at turn on of this transistor. So in this case, we have a self-commutation, the diode is turned on, we have no problem of this reverse recovery, we don't have the problem of discharging these capacitor, everything is done in a soft way. And this, of course, reduces very much the switching losses. So this is the advantage of the BCM approach, and then we turn on the transistor at zero voltage switching because the diode was conducting and the voltage is already low, and then we turn on the transistor and the current reverses again to the normal range, and it starts climbing up at the point that we have the gate. This is the gate of the lower transistor, which is turned on here, while the voltage, here it is already low due to the conduction of the diode. However, pure BCM have some drawbacks. First of all, due to the very high ripple, we have high RMS current in the inductor, and in fact in the transistors. There's a high ripple, and the RMS is also, of course, high. And also we have a DC current in the inductor. So we have here an inductor, although the inductance is smaller, but the size of the inductor is, of course, not just the inductance, but also the RMS and I peak are affecting the size. And since the I peak is high and the RMS is also high, and therefore this is going to be a fairly large inductor, although the inductance is relatively small. So these are the drawbacks of the BCM, and the idea of the triangular current injection is trying to overcome some of these drawbacks. And here is the concept. Here we have a large inductor. Well, I'm exaggerating, or maybe we don't need that much, but just to demonstrate the point, this is a relatively large inductor. Then we have another inductor, a smaller one. This is for generating the ripple. In other words, here we have almost DC with a little bit of ripple depending on the size of the inductance of this inductor. And here we have a much larger ripple. Interesting to note is the following. At steady state, the average voltage on the inductor is 0. So the average voltage here is actually V in. Consequently, since the average voltage on this inductor is 0, this is also V in. So you see that this inductor and this inductor are actually subjected to exactly the same waveform. Okay, here we have a pulsating waveform. Here it is. We have a pulsating waveform. Here we have V in. Here we have V in. So consequently, we have the same situation in these two. In fact, it is exactly like the case of the BCM, because in the BCM we also have the same waveform. So consequently, the ripple that we generate here is a function of this pulse waveform, and it is actually like in the case of the BCM, because the BCM we have a small inductor here. The difference being that in the case of the BCM the current is flowing through the inductor, while here we have a pure AC, that is, it will be around zero, because we have here a capacitor, so there's no DC current here. So just to summarize, what is been done here, we have a larger inductor so that this inductor is just carrying primarily the DC current, so it can be an inductor for a lower frequency using perhaps amorphous core and some other means that are less effective for the high frequency AC, but here we don't have a large component of an AC. On the other hand, this one has no DC, so we are not pushing the magnetic flux up on the BH curve, and consequently this will be a smaller inductor than it will be in the BCM. As far as the ripple, it's the same thing, because they are subjected to the same waveform. And here is a simulation run of this situation. This is the main inductor, the larger inductance inductor. We see this is the DC current, and here we have small ripple. Here we have the ripple of the smaller inductor, and then at this point we combine the two, so this point now sees the ripple plus the DC. So if the magnitude of the ripple is made correctly, we can get this current reversal, and therefore this converter will operate like in the normal BCM, except that the current that the midpoint sees is now not just the inductor current, but actually it's coming from the two inductors and being combined to get what we need for soft switching. So this is the idea. Now, in order to demonstrate it, I've sort of set up you might call a poor boy control design for this thing, actually to run it correctly and to make sure that the ripple is correct, and also to reduce the harmonics in the case of power factor correction. I'll talk about it in a minute. Then you probably will need a microcontroller for that. This is just too complex for an analog circuit, and in fact in the realization that I'm going to show later on in part 2, the design is based on a microcontroller. So just to demonstrate it, I've done the following. I've set up here a flip-flop to change the drive of these two transistors, and the condition for this flip-flop to move from one case to another, that is for this transistor to go on or this one, is the following. If the current of the inductor is reaching the value of a scaled Vin, and the scaling is per the power that you need, so this is now this ripple represent plus the DC represent this input current. So once this input current is larger than this scaled Vin to keep a given power level, then it will kick and it will change the situation of these drives. And the second condition is that if the current, the combined current, is passing the negative side, that is below zero, for a given magnitude of zero value, then it will kick back. So we have here like two thresholds One that will keep the current, the input current, actually with this shape, because it's always clamped to the profile of the input current. And then on the other side, it'll clamp to 0 with a little bit negative value to get the soft switching. So this is this flip-flop, and these are the conditions here. This is one condition, this is the other condition. This is just drivers to set and reset this flip-flop. Again, this is just for a demo. Let me just point out that if it is used for a power factor, for example, and this is the example I'm giving here, this is supposed to be a rectified input, okay, this is a rectified input. Then what we are doing here, we're actually adjusting the peak value to follow the input, while in fact we would like to have the average value following the peak or the V-in. So it's not exactly what we need, and therefore the THD will not be perfect, but still, just for the demonstration, I'm just showing the circuit, because otherwise it's just too complex and I just don't have the time to set up a full-fledged controller for this circuit. Okay, so this is just a demo circuit. Again, I'm using here a rectified input. In reality, we don't need actually a rectification, because we can use either a full bridge here, I'll show it later on, or a totem pole, which get rid of the diodes here, or the rectification. So it's a diodeless realization. But this is again just a demo, so let me just go over it again. We have an AC which is rectified. We have the peak current here, which is the low frequency following the input, okay? And again, in order to simplify the control, I've put here a DC. In reality, this K has to be changed in order to accommodate the exact output voltage that you need. I don't have it here, this is just a DC. So the input is following the input voltage, I mean the input current is following the peak of the input current is following the input voltage, while the negative side here of this ripple, this side here, not here, but here already, after combining this with the ripple, I'm making sure that it'll pass the 0, so it'll be negative. And here is the overall result. This is already the inductor current. So we see here the ripple, and again this upper side is following the input, and this is now the combined signal or combined current of the input plus the ripple coming from the small inductor. Okay, so this point here, let me go back, is this signal here. This is this plus this. The upper one, the green one, is the current of this inductor, which shows here. Okay, and then if I zoom in, here is what I see. This is the input current. Again, it's a DC with a small ripple, and here is the combined signal of the input plus the ripple, and here we see this negative portion here, which helps us to accomplish 0 voltage switching and turn on of the lower transistor. Okay, so this is the idea behind this approach. Now in part 2, I'm going to show some application as published in some papers, and also I'm going to evaluate this approach against conventional or other approaches to see how good is it in various aspects. And here I'm going to give a very short introduction to what I'm going to show in detail in part 2. So the first paper I'm referring to is a paper by Professor Kohler and some student of his group. And this is a rectifier again, power factor corrected. Here they're using a full bridge. In the case of a full bridge, you do not need a rectifier because a full bridge can accommodate both a positive and negative voltages. Here we see the inductor, main inductor, and here is the auxiliary inductor plus capacitor, which is a little bit problematic because this capacitor has to, of course, carry the ripple current, so it's not a little capacitor, it's a pretty hefty capacitor. So this is one approach. And then there is another approach, which is actually a reference designed by Texas Instruments, but it is described in this EDN article. Here are the details here. This now is a totem pole, in which case, again, we see here the inductor and we see here the inductor. It is a interleaved configuration, two half bridges here. These are GaN transistor, gallium nitride transistor, fast transistor, and this is, in this approach, totem pole used for actually polarity selection. So in this case, you don't need again rectification, because you might say that this arrangement, this is like diodes, is except that the voltage drop, of course, is lower because these are transistors, but this actually helps to sort of provide positive signal here always to the output. So these are two approaches and two designs that have been published that I'm going to discuss in more detail in part 2. So let me summarize this part 1. We see that the BCM can be achieved by triangular current injection. It requires two inductors, one high ripple and no DC, and one of small ripple with DC. And then it needs a blocking capacitor to carry the ripple current. And then the injected peak current needs to be equal to the average input current, okay? In order to make sure that it's about equal, make sure that you have the negative part. And then the inductance of the auxiliary inductor need to be similar, in fact, to the inductance of the conventional BCM, because they are seeing the same waveform, the same PWM waveform as I have shown, and therefore the operation is just about the same, except that in this case, of course, it does not carry the DC. And then the amplitude adjustment of the injected current is actually accomplished by frequency variation. In the design, control design, the pool boy control design that I've shown, the frequency variation is done automatically, but in a microcontroller approach, you might wish actually to control the frequency. Anyhow, there are different ways to do that. A major benefit of this ripple injection approach that needs to be emphasized, and perhaps this would be the main reason to go to this configuration, is the fact that we have here low ripple, and therefore there's a low ripple injection into the source. This is very important because in order to pass EMC norms, one has to put actually filters in order to reduce the ripple injection into the line. And since the ripple here is appreciably lower than in the BCM, then obviously you'll save a lot of this filter, and this could be the reason to go to this approach, which on the surface looks as if it's more complicated and perhaps more costly because you have two inductors. But again, if you take into account the whole system, then this could be really competitive. So the part 2 includes the example of this published application and the evaluation or comparison to other approaches. So this brings me to the end of this presentation. I hope you found it of interest. Thank you very much.